Friday Stand-In on 702, your number one news and talk station.
Welcome back. 6 minutes past 10. My name is Chris Vick. I'm the Friday Stand-In, and it's going to get confusing. We're going to have Chris talking about some medical stuff. Chris, welcome. I believe you're around every week.
Oh, hi, Chris. Yeah, I pop in. Yeah,
pop in, but I can't see you. Is that because you're naked? You sort of work from a booth?
Yeah. I hide behind the screen. That's right. I pop in on Fridays, and we're doing any science question on anything that anyone wants to talk about. And in fact, I actually got this lovely email here from Marie Anne Denise, and she says, I manage an aftercare in Cape Town, and I listen to your show on Cape Talk on Friday mornings. One of my students, Zach, wants to ask a question. He says, if the ice caps melt, they will dilute the salt water because they're made of fresh water. So if the ice caps are made from fresh water, how did they form from a saltwater ocean in the first place? So that's the calibre of the kinds of questions we're getting in and the kind of bright people who are listening. I will tell you, Zach, it's an excellent question. And the reason for this, chemists use the same science all the time to purify things. What's going on in the sea is that you have an ocean full of salty water. When you lower the temperature, the water wants to freeze, but the structure of ice has the water molecules arranged in just the right orientations relative to each other. And the salt particles are a different shape, a different charge, and they don't fit the shape. So it's a bit like jigsaw pieces, which have to go in the right place at just the right angle to fit to make the jigsaw picture. An ice crystal is the same, and only water molecules can fit in, and only water molecules at the right angle can fit in, which is why freezing an ice takes a while to form, but which is why even in salt water you will get freshwater ice, because only the water molecules fit the crystal. Okay,
I have an even more pertinent quick question. Why, when I put Russian vodka in my deep freeze, does it not freeze? I like the fact it doesn't freeze, but I'm curious why.
Yeah, well, the sea has to get very, very cold before it begins to form water ice. But when you add things to water, those particles, whether it's salt, whether it's alcohol, they are getting between the molecules of water. And eventually you get to a point where the concentration is so high that those, in the case of your vodka, those are ethanol molecules. They're getting in the way of the water molecules being able to form crystals at the right angle. So you could freeze vodka, it would work, but you would have to make it really, really, really cold. So if you had a powerful enough freezer, you could actually get it to freeze. You can freeze alcohol. It goes like a gel and then it goes, rigid. But it has to be extremely cold. And the reason is that you've got to work harder to get the alcohol molecules away from the water, because everything's trying to stick to each other. And if you have a high concentration of alcohol, the chances of a water molecule finding another water molecule at the right orientation to form an ice crystal is much lower than the chances of an alcohol molecule getting in the way and stopping the freezing process. And that's what's going on.
That's fantastic. I'm gonna remember that next time I open a bottle of Beluga. But there's something you want to talk about in terms of lobsters and jellyfish, right? I mean, jellyfish, we all know they can cause a very nasty sting. But apparently there's some research around the fact that baby lobsters are actually immune to being stung. Just talk us through that one.
Well, this is research from Japan, and the motivation for doing this is that A, we want to understand ocean conservation and marine science better. B, we want to work out how to farm marine creatures better, because at the moment we are depleting the sea, taking fish out of the sea to feed farmed fish. I mean, it's completely nuts. So scientists are looking at how creatures grow, evolve and feed themselves in the ocean naturally to work out how we might be able to recapitulate that more efficiently on land. And lobsters have an interesting story to tell, because lobsters, when they're first hatched, they form a larva and it floats through the water, and these larvae actually find themselves a jellyfish, and they stick onto a jellyfish, and then they eat the jellyfish while it's still alive and while the lobster is developing. But the big question is, well, lobsters, everyone assumed, were immune to the stings of jellyfish, but they're not. So how on earth do they eat the tentacles of jellyfish and not get a very painful rear end when nature takes its course, and potentially fatally? So this group of researchers at Tokyo University's Institute of Marine Science, what they've done, and this is a person who is called Michiya Cameo, and they've got a paper in the journal Plankton and Benthos Research. What they've done is they went to the market in Tokyo, found some fishermen who'd recently landed a female lobster that was bearing lots of eggs. They put the lobster in a tank, they grew lots of little baby lobsters from the female lobster, and then in bags, so they could watch what was happening, they fed them on a diet exclusively of sea nettle tentacles. Now, these are jellyfish that have big stingers, so these lobsters were eating stings, and they didn't get stung. They didn't actually get any problems with their intestines. How were they doing it? Well, the researchers painstakingly pipetted out what came out of the rear end of the lobster as it pooped, having eaten these stings. And they found that the lobster guts wrap up the contents in a special bag or membrane. It's called a peritrophic membrane. And this does not get in the way of absorption of nutrients or the digestion of the food, but it keeps other structures like the nematocysts, which are the miniature hypodermics that are in the jellyfish stings that enables them to sting. It keeps them sequestered inside this bag so they don't discharge into the flesh inside the lobster, so it can eat the tentacles with impunity and no risk of a sore ear end.
Sounds like an in-house pamper, though.
Well, insects do the same thing, actually. People knew that insects do this. They have sensitive guts, and so they wrap their diet up in a sort of string bag made of chemicals. No one had anticipated that lobsters may do the same thing. Now we know that they do.
That's fascinating. Remember, you can have a chat with Chris as well. You can give us a call, 011-883-0702 or 021-446-0567. Sam in Brooklyn, you seem to have a similar train of thought as me, right? What's your question?
Hi, Chris. I just want to know, when I open a bottle of my favorite bubbly, and on the rare occasion that I can't finish it, all I do is I pop a teaspoon in the top, and it keeps the bubbles for up to a week. It befuddles me as to why it does that. It just doesn't go flat.
You have champagne. You have champagne open for a week, Sam.
Well, no, as I said, on the rare occasion that I don't. But
okay.
I was more bothered by the fact that Sam has champagne left. What's that all about?
I just want to know how it keeps the bubbles. If you haven't got a stopper. But if you don't put in the spoon, then it goes flat the next day.
Chris,
Hi, Sam. Well, I'm really sorry to burst your bubble, but it is a myth. It is not true, and it has not stood the test of scientific scrutiny. And in fact, people have done research on this to find out whether it's true or not, and there is no evidence whatsoever that bubbly stays more bubbly if you put a spoon in the neck. There's no reason scientifically that should be true. The bubbles are carbon dioxide. The bubbles form when the champagne is being fermented, and the champagne or bubbly maker, they add sugar late in the fermentation and then recork the bottles, and this drives a secondary fermentation, and because the gas, the CO2 which is made, cannot get out, it's forced to dissolve in the liquid. When you take the pressure off, that's what's holding the gas dissolved, it enables the gas to start coming out, which is why it froths out. The only way to keep the gas in the drink is to repressurize the bottle. And so some of these fancy wine storage devices you'll see come with a sort of built-in pump so that you can put the cork in and then pump something inert, CO2 or nitrogen, into the headspace above the wine, and this will stop the gas coming out. Best thing to use is CO2 because that's in there in the first place. Problem is that you may then begin to adjust the acidity of the wine. The best option, I'd say, is just to drink it first off quickly.
Great.
Would you agree with that, Chris?
You're the kind of scientist I can connect with. Carol in Midrand, do you want to have a quick chat?
Yes, good morning, Chris.
Morning.
What I want to know is, you get a twitch in your eye sometime, and it's sort of like a nervous twitch. What causes that? And how can you get rid of it?
It's a real nuisance. And the way it happens, the muscles all around your body, your somatic muscles, skeletal muscle, they are supplied by motor neurons, motor nerves, which are in your spinal cord or in the brainstem. And the motor neuron has a connection from the brainstem or spinal cord out to the muscle, and it divides and supplies a squad of muscle fibres. And normally, when you want to make that muscle move, the motor neuron fires a barrage of nerve impulses. They hit the muscle, and they electrically excite the muscle and make it move. For some reason, in some people, the motor neurons, not all of them, but a small subset of them, start to discharge electrical impulses spontaneously. And this causes the cluster of muscle fibres that the motor neuron supplies to contract rhythmically, and that causes that twitching sensation. It tends to be more common in people who say they get this a lot. It tends to be more common when people feel tired. It tends to be more common when people feel stressed. And it tends to be more common if you've had too much coffee. And coffee potentiates the action of adrenaline in your body. It increases the adrenaline signal. So it sort of does the same thing as putting you in a stressed state. So it's probably excitability. It's an excitability of the motor nerve. And that's just firing off these impulses. The good news is that usually it's not something that a good night's sleep won't remedy. There are other more serious reasons why this happens, but it doesn't just happen in one tiny patch occasionally. And in the serious reasons that it happens in many muscle groups all at the same time, and it's pretty obvious there's something going wrong. But the odd eye twitch is not harmful. It's usually just, it will sort of rescind itself spontaneously with some rest and a bit less coffee.
Oh, wonderful. And stress. I think it's more stress at the moment with me. Thank you so much. I really appreciate
You're welcome.
your help.
Thanks for the call, Carol. David in Ilovo, welcome to the show.
Hi, good day, Chris. Both Chris's.
Hi, David.
Just a quick question, actually. What's your take on flat Earth? And the reason I asked the question is actually from your first question you started the show off with. Either it's a conspiracy theory or whatever, but especially around the fact that the curvature of the Earth, apparently things should go over the horizon. However, if you always increase the power of a telescope or binoculars, you're still able to see such objects. So what's your take on the flat Earth theory? Yeah.
No, the Earth is a ball, and the evidence the Earth is a ball is if we look at other planets in our solar system, then we see that they're a ball as well. If we look at the Earth from out in space or the surface of the moon, it's a ball, and if you look at the moon, it's a ball. The reason that they formed balls is that when our solar system was forming in the first place about 4.5 billion years ago, then the material that formed all of the planets was a big ring of gas and dust, a bit like the rings that you see around Saturn today, and out of that coalesced planetesimals, baby planets, and from those grew big mature-sized planets. And they are forming under the influence of gravity. Gravity is the attraction between mass, and gravity wants to act in such a way that it pulls all of the mass as close to other bits of mass as it can. The best way to achieve that is with a spherical shape, where all of the matter is as close to other matter as it can be, and hence planets form broadly spherical shapes. When one looks at the horizon, you can actually estimate how far the horizon is by using the 1-2-4 rule. So what you do is you take the height of your eyes above the ground sea level in feet, and you take the square root of that and times it by 1.24, and that will tell you roughly how far it is to the horizon in miles.
That's fantastic. That explains. I've seen pictures. That's how I know the world isn't flat. But I think you gave a much more detailed answer. Thanks for the call. Ramodongwane in Tswana, you seem to have a similar problem to me, right? You spent too much time analyzing alcohol.
I did indeed. However, I do appreciate the molecule and the crystallization and all of that stuff. My question is the ale family, the beer and the cider. Why do they freeze? I can from my own thinking, analyze it and say in terms of there is more water content there, but I just need a scientific response. Why do beer and cider freeze if vodka and other whiskeys do not freeze?
The difference is that the average beer has about 4 or 5% alcohol content. The average decent vodka is 50%. So in other words, there's 10 times as many molecules of alcohol sitting in there as in the spirit than there is in the beer. And therefore the energetics, getting the water molecules to bump into other water molecules at the right orientation and not be pulled away by an alcohol molecule getting in the way, that balance is far more favourable for freezing beer than it is freezing spirits. Now, when you freeze the beer, you will still freeze the water in the beer. So if you freeze your bottle of beer, you will end up with a much stronger beer because what's left behind will be a higher concentration of alcohol. It won't freeze completely. There will still be liquid there. And that liquid will contain a higher ratio of alcohol to water. And in other words, you will make ice in the beer until the ratio of alcohol to water becomes capable of preventing or impeding the formation of further water crystals or more ice. And this is called ice distillation. I'm not sure it's legal to do that because you are distilling alcohol, but it will certainly make your beer stronger.
You know, I had a beer called King Cobra, which is sort of the upgraded version of something called Cobra. You can't buy it anymore, but it was 10% alcohol content. It used to knock people flat. Would that level of alcohol content make a difference in terms of freezing? Just for future reference.
Well, you can freeze wine. I have accidentally done this when I have had a dinner party and forgotten to put the wine in the fridge, or there wasn't enough room in the fridge, so I thought I'll just put the wine bottle in the freezer temporarily before we open it ahead of dinner, and then you forget because, you know, something else happens, and then you go, oh dear, and you go and find that your bottle of white wine is now completely solid. And so wine is running at 10 to 14%, give or take, and so that will still freeze. It's once you get beyond the 20-30%, I think you start to have problems of making it freeze.
Just as a matter of interest, do you find wine tastes different once it's been frozen? Do you think it affects the taste?
Well, the purists are going to tell you that it will, because when the treatment that a wine receives, both when it's a grape on a vine through to it being juiced and then fermented and then bottled and how it's kept, those things make a huge difference to the character and the enjoyment of a wine. Some wines are more sensitive than others, and so some wines you might get away with it, but I think most people would say if you mistreat a wine like that, you're cruising for a bruising, because it's not going to taste how it should, because you probably are going to encourage other there are other chemical reactions that you'll probably encourage. There are other volatiles which will react in different ways because concentrations are being changed by that treatment, and that's going to cause the wine to lose a lot of its special character.
This is really crucial information. I hope all the wine o'clock people out there are listening. Ronald in Cape Town, you want to change the subject a bit. Why?
Thank you very much. Good morning. I have an interesting question. I sincerely hope that you will be prepared to answer it. It's about cricket. A bowler, the ball leaves his hand, and we are told and on the screen that the ball is traveling at 145 k's.
Mm-hmm.
He hits the ball to the boundary. It's a little 8 diameter ball. The fielder chases after the ball, and that ball outruns him. So what speed can that ball be rolling at if the bowler is bowling it at 145 k's?
Well, you've got to remember that although the bowler sends the ball towards the batsman at that speed, I should say more accurately velocity, because the ball is going in the opposite direction to the direction the batter is going to hit the ball. The ball interacts with the bat. The bat absorbs the energy, the momentum in the ball, which is carrying the ball towards the batter, and it then imparts new momentum to the ball, which is energy being transferred. The bat is doing work on the ball to give the ball a push out into the field somewhere. So it doesn't really matter what speed the bowler throws the ball at. The bowler just wants to get the batsman out. So he wants to make a ball that's very hard to hit, hard to predict, but is on target and will take down the bails off the stumps. The batter wants to send the ball as far away as he can, so he or she has got the chance to run as far as possible and get as many runs, right? Or even a six. So actually, it's all about using the bat as a hammer to get as much energy into the ball once you've hit it, but the bowler is a different story.
That answer your question, Ronald?
Thank you, William. Thank you.
I think the best advice is stay out of the way. Hey, you don't want to get hit by a ball at that speed.
All right.
Thank you for the call.
So much.
Appreciate that.
Appreciate it. Bye-bye.
Janice and Clement, welcome to the show.
Hi. Good morning.
Morning.
Morning, Janice.
My question was, can you explain the phenomena of the Sprockton spectre? We experienced this on our way back from St. Helena, and we all had halos over our heads, rainbow halos over our heads, but you could only see your own halo. You couldn't see the person next to you. It was on the sea. We could see our shadows, and our shadows actually had a halo over our heads. What causes that? How does it come about?
I haven't heard of this. I've not heard that word, but I think I know what you mean. If you are seeing a rainbow effect, then that is an effect called refraction. The light coming from the sun is white light, but white light doesn't exist. White light is our perception of when all of the colours that you see in a rainbow are mixed together. So you can do a party trick on somebody. You can hold up a piece of red paper and a piece of white paper, and you can say to them, which one of these has got more colour in it? And everyone will pick the red one, and you say, no, it's the white one, because actually that is reflecting all of the colours of the rainbow at you, and your eye interprets white or all of the colours mixed together as white. Now, when you see a rainbow, what has happened is that all of those separate colours have been refracted, bent by something. The commonest way this happens in the atmosphere is by a rainbow, and that's raindrops. And it is exploiting the phenomenon that when white light, which is a mixture of all these different colours, goes from one medium, air, into another, that's water, then you split the white light up into all of those different colours because they all get bent a little bit more by going from the air into the water, and that splits them up. Now, for you to be seeing that halo effect argues that there must be something behind you which is splitting the light up in that way, or it's splitting the light up in the way it's being reflected back to you. I'm not sure what would account for it on the occasion you saw it, but I'll tell you what I'll do. I'll go and have a look and see if I can find some pictures and get a bit more.
Amazing pictures.
You can see the same thing around aeroplanes. I think people have told me that occasionally when you see yourself when you're flying in an aeroplane, you can see the shadow of the aeroplane on the ground. You occasionally see a rainbow effect around the aeroplane, and I suspect it's probably a similar phenomenon. But I'll have a look into it and come back to you.
Yeah, great. Thanks, Chris.
Thanks for the call, Janice. Time for one more. Sean in Joburg, welcome to the show.
Hi, just going back to your issue of water and those. The work of a Japanese doctor, Professor Inoto, on crystallization, when the water crystallization, when it's exposed to good vibrations or emotions, it forms beautiful crystals. If it's exposed to bad or negative vibrations, it forms horrible-looking crystals. Your comment on that, I'll listen on the radio. Thank you.
Thanks, Sean. Chris?
Well, Sean, I mean, it sounds very iffy to me, if I'm honest, because the water doesn't have a sense of consciousness. The water does not know what you define as good or bad vibrations. Water molecules don't have a sense of sort of ethics or a sense of taste. And so I think this is probably bunkum, to put it simply. Doesn't sound feasible or scientifically credible to me. But if anyone has a reference that they would like me to look at, please send it in. You can tweet at Naked Scientists, and I'll take a look and see if we can dig into it and see if there's any scientific basis that might explain it.
That's great. Sean, happy? Sean's gone. Chris, we've got a little bit more time left. I'm sorry, I'm going to have to abuse your presence. My wife and I are pregnant. We're due to have twins in January. And we've been having...
both of you?
Both of us are
You're pregnant as well.
I'm carrying
that's a medical
one.
miracle.
She's carrying the other. That's why I'm...
You've just been having too many beers, and that's what it is.
It's that damn beluga. You know that. So I'm this sort of. I'm reading everything I can. I'm watching every video I can to try and understand the process better. The one thing that really interests both of us is the role of the placenta. And when you were talking about the jellyfish, it got me thinking about it. One of the doctors we've spoken to says there's absolutely no problem in my wife eating sushi, for example, because if there's mercury in it, the placenta will filter that mercury and it won't reach either of the twins. That accurate?
No, probably not in that case, because the placenta is an amazing thing. And in fact, when I was delivering babies, because I've delivered quite a lot of babies when I was doing my medical student bit, and it was phenomenal to see the placenta come out. And you think that this thing, which it's like a big pancake, but really big beefy pancake about 1 inch thick, which glues onto the inner lining of the womb and supplies all of the nutrients that the baby needs. Now, the placenta is actually made by the baby, and it brings the baby's tissues very close to the blood supply of the mother, and there's a special lining of cells on the placenta which are able to exclude some things but not other things. They're very good at excluding certain types of antibodies. They're very good at excluding the wrong sorts of cells. They're very good at excluding a lot of infections. But the way I look at it is this: if Zika virus can get from the bloodstream into the baby, and Zika virus is really big, a particle of mercury is going to have no problem slipping through.
Okay.
But the placenta is an amazing thing, and we're all here because of one. And somehow it enables an organism, a baby, which is genetically completely incompatible to its mum, to grow inside its mum for 40 weeks and not be rejected by the immune system. And if you did that with any other piece of tissue, it would be dead in minutes. It's an amazing phenomenon how this works.
Chris, thanks, man. That's been fascinating. I've learned a lot. I'm sure the listeners have learned a lot too. It's been great talking to you. Thank you.
Thanks, Chris. It's been great fun. Cheers.
Thank you.